Welcome back. When we last left, we had this. And we said we could collide with the thing from the top and the bottom. But if we collided something to our left or something that was below us, we couldn't. It didn't work right. So that's what we're going to fix today. Okay, so here's the deal. Turns out, S.A.T, we really need to know what direction we're coming from whenever we do this collision resolution, because this minimum penetration vector is not exactly really signed completely. It's kind of relative to where the objects are in relation to each other. And for our situation, that's going to be our transforms for each of the objects. So we're going to have to get a vector that tells us which direction we should separate. And so we want the signs of that the sign of that separation vector. So if we go into test here, and this is going to get kind of interesting. So we want a separation, say separation direction. And really that's just going to be a vector 2, and that's going to be, so when you want a vector that points from one point, say from point 2 to point 1, so that it points from point 2 to point 1, you subtract point 2 from point 1. Hopefully that makes sense. We want a vector that points to our player, because that's what we're doing the separation on. So what we want to do is we want to do a self.transform.x here, so actually self.p, sorry. So the player, we're looking for the player, and then we're gonna subtract our missile's x, and we're gonna do the same thing for y, and that'll give us a separation vector. That'll give us the correct push, the correct orientation of the push that we want. Because if you look, let's do something fancy here. Let's say, instead of the way we've been doing it, let's do string.format. Let's print our separation vector, and we'll do %.2f, which says print a floating point value and only print at the most two decimal points, or 2 places after the decimal point. That's all that's saying. And then we'll say amount, and then %d, which just says print an integer. Which I guess we could do 0.2f for that too, really, because it doesn't necessarily have to be an integer. And then we can just wrap all this stuff up like this instead of having all these concatenations and whatnot. Feels a little bit better, but let's print that real quick. Something that I haven't made an issue. Let me bring this over. Show you what's going on. And that should be a vector 2. I'll show you what's going on here. So when we collide, actually, let's comment out the actual response, or pushing the player out of the missile's collision box. When we collide here, let me drag this over, we get a separation vector of -1, 0, and that is correct for this particular orientation here. But if you watch, I'll sweep the player all the way through, and that collision vector goes to 0 here, but that's because it's not the minimum. You can see it goes right back to -1, and this is the wrong direction. We don't want to push our player back to the left. So that's what we're going to have to do. We'll reference the center of these two guys to figure out which direction to push. Then there's another issue that we have. These rectangles, for the most part, actually completely, for the rectangles, regardless of whether they're rotated or not, there's really only 2 sides that you need to test, right? Because these 2 sides are parallel, these 2 sides are parallel. We don't need to test parallel sides. So what let's do is let's go back to the S.A.T stuff, and right above get edge normals, let's create another function, and let's look for, let's call it contains. We'll just call it, yeah, well, let's just call it contains. And what I want to do is I want to take an array of edge normals and then a potential normal. Let's call it a unit normal because it needs to be a unit normal. And let's check and see. So we're going to do for I equals 1 to edges. So what we'll do here is if we get through these and there is no, and this, we're going to check and see if this edges array contains either the exact unit normal or a parallel version of it. Because if it's parallel, it's the same thing, and we're still testing the same axis, right? An axis pointing in one direction is the same as an axis pointing in another direction whenever we do projections. So if we get all the way out here and we don't get anything in here, that means that it's not, doesn't contain this unit normal. So in order to test this, we're going to say if normal or unit normal. So what we can do is we can take the dot product of the edge, of the particular edge, and since we know these edges, because we're coming from here, remember they're edge normals, and the edge normals here are unitized, so there are unit vectors. And then we'll also make sure that when we check for this unit normal, it will be unitized or a unit vector. When we do that, the product of two unit vector, or the dot product of two unit vectors, will tell us some really cool things about how these things are oriented with each other. If we get a unit normal of 1 or -1, that means 1 means the two vectors are pointing in exactly the same direction. A -1 means the two vectors are pointing in exactly the opposite direction. In other words, they're 180 degrees apart, which means they're parallel. They're or basically it's the same axis. Okay, that's kind of what we're testing. So really what we want to do is then we want to check the absolute value of this, and we want to see if it equals -1. If it does, then we return true that we do contain, let's call it this, contains axis. That means, that makes more sense. So we're checking to see if that axis is contained. It doesn't matter if it's pointing in which direction. It's just, we just want to know, is this axis contained within this group, so that we don't test more than once. And then that allows us to come down here and say, yeah, if the edge magnitude is greater than 0 and not contains axis, and then we'll take our edge normals array here and we'll check our normal that we're thinking about inserting to see if it's already in there. Makes sense, hopefully. And that should do what we want. Now, something else I've run across a couple times and really haven't said anything, and that is, I really don't like this right here, having to do this. Really, what I want to be able to do, so edge :normal, I want to do :unit. Well, that's doable. I just have to change this vector2 to, whenever we take a normal, to just return self. And you'll see this is done in programming a lot. It makes things just, you can chain things together like this, so you can perform multiple operations on a particular object, because we go edge :normal and then it returns itself, and then I can just call that object again with another function on it. So let's also do that with unit, and we'll just return self. That way we can chain these things together. And you can use that, or you can use that or not, right? So we'll do that for these. Shouldn't affect any of that, and I think that's the only ones that we need to worry about. I believe that's correct. So now vector 268. Oh yeah, sorry. Yeah. That's a normal. Right. So it already returns itself. So really just that unit, the unit, we're returning ourself on the unit so that we can actually assign it. And we should still, yeah, see, we're still fine. We still haven't solved our problem of penetration as far as to how we should push the two polygons apart yet. We're getting to that. We will get to that. There's a couple of other places where we can, now that we've made some of these changes, that we could go and sort of make things a little more tidy like this. And as we see them throughout the series, we'll just go and maybe fix those things depending on if we actually think of it, you know. And then something else I wanted to do just for, I don't know, just because it felt better to me. And that was back at the S.A.T. we had we had a variable called overlap, and I just made it a large number, but I want to make it a just basically fill it up. Or we could even do so that's huge, right? And that's almost a complete full 32-bit number, and I'm leaving, or let's see, BEFFF. So I'm leaving the sign bit off of it, so then it would be positive. Not a big deal. It just feels better to me to do that. So we're going to do that. So with now back to, well, actually, let's check and see on get edge normals. Let's do a print real quick, and we should have half the edge normals that we were having, which would be 4 for each rectangle. And you can see here now we have 2 for each rectangle, and that's great because we don't want the same to test the same axis more than once. So that should cut down on our testing or our compute power. So let's return to the problem of figuring out which direction to push out our polygons whenever they collide. All right. So there's a couple of things we're going to need, and that is what we want to do is we simply want to test to see if each piece of the separation direction that we've just calculated here, if it is the same sign as our minimum separation unit vector. If it is, we're all good. If it's different, we want to make it the same. In other words, we'll just multiply MSUV. So let me show you. So we want something like this. We want to say if, let's say same sign. Let's do it the Lua way. Same sign, separation direction dot x and minimum separation unit vector dot x. If it's not the same sign, then what I want to do is I want to say we're going to do some doctoring on the minimum separation unit vector, because remember, this has the right sign. We know that because of the way that we've constructed this vector. So I'm going to go in here and we'll just multiply it by -1, which will make it the same sign as this separation direction vector that we calculated. And what we want to do is we want to do that for each of the pieces in the array, and we need also to do this. Yes. So that will swap. So we'll say swap signs on the minimum separation unit vector as required to push self.p. in the correct direction. I like it when a plan comes together. So then we should just be able to go back to this. Now, issue is we don't have this function yet. I want to put that, I feel like that's a utility function or it's a math function. Either way, let's make a function called u.same sign and then number 1, number 2, or we'll just do A, B. And then we'll say returns true if A and B have the same sign. Now, a great way to do this would be to use an XOR function, but Love2D, at least as of right now, it doesn't have an XOR function, an exclusive OR. It's just an exclusive OR function, and that means if you have, we'll just speak in terms of true and false. So an OR, if you have an OR, you have one or the other. So if you have a false or a true, then you're going to get a true as a result. If you have a false and a true, well, it's going to be a false because they both have to be true. But an exclusive OR says basically it takes the difference of those two items. So if you have a false and a true, you're going to get a true. If you have a true and a false, you're going to get a true. If you have a true and a true, you'll get a false. So basically, if they're different, the XOR will give you a true. But again, Lua or Love2D doesn't have an XOR function. So what we can do is just make one. So let's make one, and let's say XOR A and B. Okay, so now what we will do is we'll return the following. So exclusive OR will return not A. So these are, let's see, okay, so exclusive OR function where A and B are Booleans. We could test, but we're not going to. We're just going to assume. So we're going to return not A is not equal to not B. That will give us an exclusive OR function. So now all we need to do down here is we can return XOR. Okay, now here's an interesting thing. What we want is to know if these have the same sign. So we can check, we can say, well, is A greater than or equal to 0? So if that's true, and B is less than 0. So we want to see is A greater than or equal to 0, and then B less than 0. So if that's true, true, then they will not have the same sign. You see? And if A is false and B is, if either of them are different, we're going to get the correct answer when we XOR them together. So just hold on to your hats, please, and we will see. Let's go to our test, and we will say U. All we have to do should be is put U here, and I think if I didn't spell it wrong, yes, okay. So let's see if this actually is working. So we have we have that, we have this. Look at that. So we're all good. We're getting the correct separation direction by comparing these signs of these things, and we want to match the minimum separation X and Y with our actual separation direction vector, which is what we know is correct. I don't believe that is yes. Why would you have a not there? Good point. I don't think you need a not. So an XOR is A not equal to B. So if we have 0, let me think here. 0 is not equal to 0. Return false is not equal to false, and that will be false. Return, yeah, we didn't need that not there. Yeah, well, okay. Yeah, we didn't need the not, but we could have put it there in case the A and the B weren't Boolean. So that's kind of, I got this this function. I saw this function from some other code that I was looking at that was just talking about XOR in Love2D, and somebody had come up with this. But really, the not, all the not does is just converts those A's and B's into Boolean for you if they're not already. But if they are already, we can just do this. And we're just assuming that they're Booleans here. So we're good. And as you can see, we are actually correctly pushing the player out of that box, or out of the collision box. Let's now also undo this, run it, and watch as the magic occurs where we are actually, you see, and then he's pushing. We are, boom! This is fantastic. Now, something we can do, and we may do, there's a bunch of options here. I haven't decided which one to do. Now, you know, testing these for separating axis, there's some things that you have to do, and it can get somewhat complicated, especially when you're testing a lot of these things. And that's one of the reasons for the circle collider. Circles are a lot easier to test, so the thought is that you could actually add a couple of circle colliders and then test those first to see if they're colliding before you do the separating axis, which is more involved. We could put the circles back, right? Was it 8, 8, and then 62, 40, I believe. We'll just stick them back on there. Except I keep forgetting those commas every time we do this. Yeah. So, funny, I don't see the player's circle collider. Except, is he scaled or what? Yeah, he's scaled. Yeah, he's scaled by 4. So this should be 32. Yeah, there we go. So, nice. We have, I think, what we need, and we actually have actual oriented bounding box. And actually, if we wanted to test it, this should work for arbitrary convex polygon collisions. So we'll take that in the next episode, and we'll there's a number of things we could do. Again, we could implement a collision sort of system and then have that come up and do all the collision for us and do callbacks. We may do something like that. Yeah, we may do something like that. But in any case, we have an actual working collision system now. And we'll probably relocate a lot of this code into probably the colliders, these colliders, and we'll make them to where you can have, they can be triggers or not triggers, and they'll do callbacks and all that kind of stuff. So that should be a lot of fun. Fun. But in any case, we will see you next time, and this was a great episode. See ya.